Hi everyone, welcome to the presentation. In this project, we aim to create a frequency divider which can be programmed to divide a random input clock signal by any number from 1 to 16. The programmable frequency divider can be implemented for both analog and digital application. With simple configuration, they can be used for improving the performance of electronic countermeasure equipment, communication system, and laboratory instruments. Here is the high-level block diagram with 8 pins. Pin 1 is the power supply, 2 is the ground for all digital circuitry, 3 is the serial data, 4 serial clock input, 5 the chip select input, 6 is the ground for all analog circuitry, 7 is the digital clock input, and 8 output voltage. Low-level block diagram. It uses SPI for communication. Basically, the input is stored to the control register through the SPI. Then the frequency divider will read the divider ratio from the control register and perform the division. Next, I will talk about the SPI. SPI require 4 pins: MISO, master in slave out, MOSI, master out slave in, a chip select, and a synchronous clock. However, in this project, we only need 3 pins since the MOSI is not needed. There is only one way of communication. There are 8 bits input, so it would take 8 cycles to completely transfer data. We decide to use SPI because it has less complexity and lower power. Using I2Cs will require the address to be sent and received every time, therefore take more clock cycles comparing to SPI. Here is how the 8-bit data look like. Because we only need to divide the number from 1 to 15, and that's only require 4 bits. So the list 4 bits are used as divider ratio. Bit 4 is used as the enable bit, and the rest I don't care. Next, we are going to cover the frequency divider logic.
Hey guys, so I'm gonna describe the frequency, the method that we use for a frequency divider. Our frequency dividers or counters are formed by connecting flip-flops together, and any number of flip-flops can be connected or cascaded together to form a divide by n binary counter, where n is the number of counter stages used and which is called the modulus. The modulus, or simply model counter, is the number of output states the counter goes through before returning itself back to zero, which means one complete cycle. A synchronous divide by integer can be easily specified by using a more finite state machine. So for anyone who doesn't know what a mod n counter is, we pick a divide by 7 counter as an example. The counter will count from 0 to 7, and the picture on the left shows the more finite state machine of the counter. It has 8 possible states, and it only needs 7 states. State 1 output is 001, state 2 output is 010, and so on for all the states. On the last state, which is state 7, however, the output is 00 for the mod 7 counter. Similarly, for mod 9 and mod 11 counter, the output is gonna be all 0 for the state 9 and state 11 respectively. In the divide by 7 counter, since the output has 3 bits long, we will need 3 D flip-flops. From the finite state machine, we build a truth table with A, B, and C as 3 bits of the present state, and A plus, B plus, C plus as the 3 output bits of each state. We can easily fill up the first 7 states of the truth table following the diagram, and we don't care about the output of last state. After using K-maps for determining the smallest sum of products function, we come up with 3 equations for inputs of 3 flip-flops, as you can see on the left side of the slide. From the equations, we build a circuit on the right, and the output of block A has the frequency that we are looking for. However, that output doesn't have 50% duty cycle, and additional circuit on top will do the trick. In that circuit, adding a NOT gate on the clock will help get differential clock and a clock bar, and the extra flip-flop D will trigger the clock bar rising edge to shift the output A by 90 degrees. In addition, an additional gate will OR two outputs of flip-flop A and D to produce a 50% duty cycle output. We build a 50% duty cycle circuit in different blocks so that it can be reused in any odd integer clock division. We transfer the logic circuit to Verilog code, and instead of using Cadence tools, we simulated in free software called iVerilog. The top signal is the input clock and also the reference clock for the division. The orange signals are input and output of flip-flop A. The yellow signals are output and input of flip-flop B. And the top blue signals are output and input of flip-flop C. Since this is a divide by 7 counter, the input and output signals of flip-flop were fed into 50% duty cycle circuit, and the clock out new is the final output of the circuit.
To summarize, all circuits were built based on the Mod-N counter. To get 50% duty cycle output, we need additional gate and flip-flop. However, the 50% duty cycle doesn't always work. For example, if we want to divide by 11, 13 or 15. By applying the 50% duty cycle circuit, we just described in a couple of the previous slides, we got the duty cycle of output signal close to 50%. We guess that we need an additional flip-flop or a couple more logic gate to delay the input cycle for half of the cycle. And lastly, due to the time constraint, we are not able to transfer all of the Verilog code to Cadence tool for schematic and layout. That's all of our presentation. Thank you for listening.